Hello there, this is Alana Taki, and I'm going to be making some lecture videos here for Math 131. Now we're going to start off in section 1.1, which is talking about qualitative graphs to describe situations. So first let's think about what a qualitative graph is. A qualitative graph, in case you missed it, isn't quantitative, right? Quantitative means you have numbers, and in mathematics terms that'll be tick marks, scaling. But a qualitative graph is a graph without scaling. It doesn't have all the little tick marks on the axes, right? So if you look at this example down here, this is a qualitative graph. You see there's no scale to it. There's no 0, 1, 2, 3, and so on. Okay, that's what makes it a qualitative graph. Speaking of which, let's read this example. Let A be the average number of hours per day that Americans watch television in the year that is T years since 2000. The following qualitative graph describes the relationship between T and A. What does the graph tell us? Okay, so I've drawn this lovely graph here because I've got mad skills. And you can see that you got the T down here, you got the A over here, right? A is the average number of hours per day that Americans watch TV, and years since 2000 is the horizontal axis down here. So this graph reveals quite a bit to us. Hold on, let me pause for a second. There we go. I just needed a place to write. Okay, so what does this graph reveal to us? Let's see. Well, you can see that in 2000, over here at the start, in 2000, that's the beginning point, Americans were watching some TV, right? You're not going through 0, 0, the origin. The line starting out up here. So in 2000, Americans watched some TV per week or per day on average. Now you don't know how much it was because of course you don't have scaling. So you only know that they must watch something because you can see that the graph doesn't touch at the origin. So just on a side note, what you're working with here is the, I'm going to put this in brackets, this is the y-intercept that we're describing. Right? That the fact that it the fact that it starts at a value higher than 0. Then there's something else you see, which is that the amount is growing steadily. So since 2000, the average number of hours per day that Americans watch has been steadily increasing. And what am I getting at there? Well, in this particular case, because this one's a line, I'm getting at its slope. But I'm also just getting at qualities that the graph has. It's going up, and it's going up at a steady pace. Right? So even if it's not a line, you still want to know, is it going up, is it going down, that kind of thing. Now that leads us to a very important definition for us, which is independent and dependent variables. And as you can see, I already typed them up. So when you have an authentic situation that can be described by using the variables t and p, and that p depends on t, t is called the independent variable and p is called the dependent variable. A lot of students like to think of it, the independent variables, like the x. Now I'm going to put x in quotes because it's not always the letter x, but it's often the letter x, and the dependent variable is like your y, right? And again, we won't always use those letters, that's why I'm putting them in quotes. We change the letters, but they'll be something like that. Okay? So, for example, in the one we were doing above, it was t was the independent variable and a was the dependent variable. That happens. Okay, now for each situation, identify the independent variable and the dependent variable. Now this can get a little tricky, but what you want to think about is, it's going to be weird, but you kind of want to think about the dependent one first. You want to think about which one depends on the other one. So let C be the total cost in dollars of renting a car for n days. Okay, so when you go to the rental company, your cost depends on how many days you rent it, right? So if you rent the car for 1 day, that's a different world than if you rent the car for 17 days, right? So you can imagine 17 days is going to be a higher rental cost. Why? Well, because you're renting it more often. So in this particular instance, I would argue that n is the independent variable and then C is the dependent, because cost depends on number of days. All right. Cool. All right, now what about time? Let T be the time in minutes it takes a person to drive to work if the person travels at S miles per hour. This is a little strange. A lot of the time for us, time, pun intended, very often in this class, time is going to be independent, because time is the kind of thing that we can't control per se for a lot of cases. Much like that old song, time keeps on ticking, ticking, ticking into the future, right? So a lot of times time is independent because you don't have any control over it, especially like calendar time or what time of day it is, that kind of thing. But stopwatch time, the time it takes you to complete a task, for example, the task of driving to work, the task of finishing a puzzle, the task of, right, that kind of time, that tends to be dependent on something, right? So the time it takes you to drive to work kind of depends on how fast you drive, right? So this is miles per hour. That's how fast the person's driving. So that's independent, right? Oops, independent, right? You make a decision when you drive. It's called a little accelerator pedal, right? You make a decision with that pedal of how fast you're going to go, right? And then the time it takes you to get to school, for example, or to work depends on how fast you drove. Cool. Now, I'm going to tell you that detecting the difference between dependent and independent can be a little tricky. So what you want to do is you want to kind of think to yourself, which one depends on the other one. It's kind of weird, but you kind of want to look for the dependent first, because the time it takes to get to work will depend on how fast she's, driving. Cool? Or he's driving. It doesn't say. All right, now let's talk about intercepts. Intercepts are a big deal for us. They're going to be where your line or curve or whatever intersects with the axes. So for example, this particular graph has a p-intercept because that's a p-axis, and a w-intercept because that's the w-axis. A lot of times it'll be x-axis and y-axis, so you'll have x-intercept and y-intercept, but it doesn't have to be that way, right? It depends on which variable letters they're using. So in graphs, the way we describe the values, that's a typo, we describe the values of the independent variable along the horizontal axis. Some students think the x-axis, and I know what you're getting at, but it's the horizontal, it's the x-axis, right? So when you think of x, you're thinking of horizontal, right? That's your independent variables. You put your independent variable down there, and then you put your dependent on the vertical or the y-axis, right? Which is this one right here. So in this case, it's the p-axis. So I guess if I was going to do this correctly, I should put these in quotes, because it's not always the y. It's whatever letter they give you. Sometimes it's x and y. A lot of the time in an algebra class, it's x and y, but it doesn't have to be. All right, next we are going to sketch a qualitative graph that describes the relationship between the two variables. All right, let me pause and I'll be right back with a graph. Okay, so I drew the two axes, right, the horizontal and the vertical, and now I've got to decide which one's the dependent and which one's the independent. So I've got my V and I've got my N. So the volume of the balloon depends on how many times you've blown into the balloon, right? So when you haven't blown into it at all, your volume's going to be really low, right? And then as you blow more and more and more air into it, it's going to increase your volume, right? Now, it won't be a perfect line, but I'm going to draw it as if it is, just because, for the sake of my own sanity. But it's going to start at 0, 0, though, because when you haven't blown into the balloon at all, it doesn't have, the air inside doesn't really have much volume, right? Technically, there's a tiny bit of air. It's not like it forms a vacuum when you don't blow into it, but suffice to say that it's not a lot. So I'm going to make it start off really close to the origin. And then I'm going to make it increase, because as I blow into the balloon, more and more air goes into the balloon, the volume of the balloon goes up, right? And again, it would technically be like more like a stair step, because you put it in and then it just sits there for a second, then you put more air in and then it sits there for a second, then you put more air in, right? But I didn't have the ability to do that. All right, so now a person decides to get into shape by running 3 miles each day. Let T be the amount of time it takes a person to run 3 miles after training for N days. Okay, so let me make this lovely graph right here. Okay, so now which one's the independent variable and which one's the dependent variable? Well, you have control over how much you exercise, right? So you train 1 day, 2 days, 3 days, and so on. And then your running time, again, this is a little bit weird, but the time on this one is actually dependent, because how long it takes you to run something kind of depends on how much you've been training. Like for me, it would take me forever because I don't train, right? But if you're a person that trains a lot, then it would take you less time. So if you start over here on the left, you say, okay, over here, how much is this person training? Their N is 0, right? They haven't trained at all. That's me. So if you take your N as 0 and you start there and you say, okay, well, my N is 0. I haven't trained, so it's going to take me a really long time to do this. Now, as N increases, as my number of days of training increases, so I start training 1 day, training 2 days, training 3 days, 4 days, 5 days, so on, it's going to take me less and less and less time to do this. Now, should I make it go down all the way to the x-axis? Well, no. I mean, you're running 3 miles. It's going to take you time. So you can't make it go all the way down, but you can make it decrease, right? So the more you train, the faster you're going to do this. So your time's going to decrease, but it's never going to go completely down. Even Olympic athletes have to take time to actually run 3 miles. They can't do it like magic. All right, a couple other definitions. If the graph goes upward from left to right, like this one right here, that first one for A, we say that it is increasing. Oops, increasing. And if the graph is going down from left to right, we say that it is decreasing. Now notice you always read a graph from left to right. Did you catch that? You read it like you read a line of English. I mean, when you read this line, you say a person decides to get into shape. You're starting at the left and working your way to the right. We read graphs the same way because the person that thought of these graphs was French, and French read the words of text the same way we do. If the person had been, say, Arab, then they'd probably go right to left, or Chinese, they go top to bottom and right to left, right? Okay, so then label the graphs in example 3 as increasing and decreasing. I'm just going to do it down here. So A was, here, there it is. All right, let me put it in here. All right, so this one was increasing, oopsie, because it was going up from left to right. And then the one down here is decreasing. All right, we're all done with section 1.1. I hope that's helpful, and I'll see you back here for the lecture notes on section 1.2. Looks like we got some fractions in there. That'll be fun. All right, I'll see you then.